This lesson on the mechanics of flight deals with the forces and factors involved in flying a level, balanced turn. For an aircraft to change direction, it requires a force that will deflect it effectively towards the centre of the arc around which it will fly. This force is called the centripetal force, that is, centre-seeking. As you can see from the diagram, with the aircraft banked, the lift vector is also tilted, and it is the horizontal component of lift which causes the aircraft to turn by providing the centripetal force. If the aircraft is banked and the angle of attack is maintained at the same value as in straight flight, the vertical component of lift would be insufficient to balance the weight, and the aircraft would descend. As the angle of bank increases, the angle of attack must be increased to achieve a greater total lift, with the vertical component being large enough to balance the weight and maintain level flight, and the horizontal component providing the centripetal force. In a steady level turn, if thrust is ignored, lift provides the force to balance weight and the centripetal force to turn the aircraft. If two different aircraft can fly at the same TAS and angle of bank, their radius of turn will be the same, since radius of turn is independent of weight or aircraft type. However, not all aircraft can reach the same angle of bank at the same TAS. With a heavier aircraft, the vertical component of lift required increases, but the centripetal force necessary to maintain the same radius of turn also increases in the same proportion. The lift required, although greater, has the same inclination to the vertical as before, and the bank angle is the same. Rate 1 is 180 degrees per minute, or 3 degrees per second, and rate 2 is double that, at 360 degrees per minute, or 6 degrees per second. Rate 1 is the standard turn rate for instrument flight rules. A useful rule of thumb for calculating the angle of bank required to achieve a rate 1 turn is true airspeed over 10 plus 7. For example, at 150 knots TAS, the bank required is 22 degrees. As you have already seen, in a bank turn, the lift must be increased to provide not only centripetal force from the horizontal component, but also a vertical component sufficient to balance the weight. As bank is increased, the total lift required, and thus the load factor as well, must increase to maintain the vertical component's value for a level turn. The load factor, or G in common parlance, is the relationship between total lift and weight, can be expressed in the equation load factor N equals lift over weight, which equals 1 over cosine phi, which equals secant phi. The trigonometry of this is fully explained in the lesson on stalling. The relationship can also be shown graphically, and the chart is valid for any aircraft. It can be seen that the curve is exponential, that is, the G increases at an increasing rate with angle of bank. The point to remember is that in a level turn, load factor is a function only of bank angle. Constant bank, constant G. There are certain limitations which can restrict the performance of an aircraft in the turn. For each aircraft type, there is a design limit load factor. For modern high-speed jet transports, the limit is 2.5 G. From the graph, it can be seen that this occurs at 67 degrees of bank, which will determine a turn radius dependent on the TAS. This will be the minimum radius possible without exceeding the G limit. If speed is kept constant but bank is increased, the angle of attack must be increased to provide the further extra lift required. At the stalling or critical angle, no further increase in bank or decrease in radius is possible. Since stalling speed varies with weight and G, this limit will be a function of those two factors. The extra lift required during a turn will result in greater induced drag, so to maintain the straight flight speed, more thrust is required. As more bank is applied, more thrust is needed, and eventually maximum thrust will be reached. At this point, it is not possible to increase the bank or decrease radius. Whether this thrust limit or the maximum load factor is reached first will depend on the G limit and the thrust available. If the thrust available is adequate, the minimum radius of turn occurs at the intersection of the stall limit and the strength or load limit. The speed at this point is VA, the maximum maneuvering speed. The heavier the aircraft, the greater will be the minimum radius of turn. There are several factors which can cause uncoordinated flight: adverse aileron yaw, engine torque, gyroscopic precession, and spiral slipstream from the propeller, and asymmetric flight, plus, of course, unbalanced control movements by the pilot. Uncoordinated flight exists when the aircraft is side-slipping, and indication to the pilot of side-slip is given by the inclinometer portion, the ball, of the turn coordinator. The miniature aeroplane indicates rate and direction of turn, but not angle of bank. The level index shows when the aircraft is not turning, but not necessarily when the wings are level. When the miniature aeroplane's wingtip is against either of the rate 1 indices, the aircraft is turning at rate 1 or 3 degrees a second. A reminder of rate 1 is below the ball, 2 min, referring to the fact that a full 360-degree turn at rate 1 takes 2 minutes. The inclinometer, as already mentioned, shows the pilot if his turn is balanced. Coordinated or balanced flight is maintained by keeping the ball centered between the reference lines with the rudder. If the ball is out to one side, rudder pressure should be applied in that direction. Stepping on the ball is a useful way to remember which way to push on the rudder pedals. Side-slipping towards the center of the turn moves the ball to the inside of the turn, and vice versa. Changing the angle of bank can also restore balanced flight, but will alter the rate of turn. The second instrument here shows an uncoordinated turn to the right, with the aircraft side-slipping towards the center of the turn, a slipping turn. Right rudder or less bank would balance the turn. The third instrument also shows an uncoordinated turn to the right, with the aircraft side-slipping towards the outside of the turn, a skidding turn. Left rudder or more bank would balance the turn. This concludes the lessons on turning flight mechanics. The flight mechanics series of lessons concludes with the next lesson on